We can apply diagonalization to the systems of differential equations. So first, we must understand what differential equations are. If we have an example here that says f1t is the function of population of city 1 at the time t, and f2t is the function of a population of city 2 at time t. So the derivative of f1 tells us how fast the population of city 1 is increasing or decreasing at time t. When 5% of the population of city 1 is moving out from city 1 to city 2, and 2% of the population of city 2 is moving to city 1. And the same applies for the derivative of f2. And so our goal is to find f1 and f2, which are the functions of populations of city 1 and city 2 respectively. We can generalize this to the linear system of differential equations. So we don't just have f1 and f2 anymore. Now we have up to fn. With this is the matrix form. These are the derivatives. This is the coefficient matrix like 0.05 and 0.02 that we saw before. And this is a column vector of the functions. We want to find the functions. And this whole thing is written as f prime equals to af. Why eigenvalues, eigenvectors, and diagonalization are related? Previously, we saw that the derivative is equal to a constant times f1 plus a constant times f2. But really, the simplest case is the derivative is equal to a constant times only a function ft. And so we let gt be another function that is ft times e to the power of minus lambda t. And then we can apply the product rule and the chain rule when deriving this function. And when the derivative is 0, that means that function is a constant. So ft times e to the power of minus lambda t is a constant. And we can move this term to the right side, which will give us e to the power of lambda t times a constant. That will give us ft. So this is just a function ft. And if we account for all the functions f1 to fn, this is what we will get with the column vector of all constants. So all solutions to f prime equals af is f equals to c times e to the power of ax or lambda t in our example. And so if we derive both sides, we'll get f prime equal to af as we proved initially. And when we derive this whole term, again applying the chain rule, will give us lambda times this whole term again. And remarkably, this whole term is again the ft as we just proved in the previous slide. So this is also the definition of eigenvalues and eigenvectors as we have studied before, the similar form to this. So now our problem is really just finding the eigenvalues and eigenvectors. So how are eigenvalues and eigenvectors used in our general method? So we are given a system of differential equations with specific coefficients, and we are asked to find a general solution to the system, which are f1, f2, and up to fn. So with the boundary conditions, f1 at A is equal to b1, f2 at A is b2, and so forth. So first, we will construct the coefficient matrix A. And then we can find the eigenvalues of A by setting the determinant of lambda I minus A equal to 0. So we can find the values lambda as the roots. We can substitute each calculated lambda I into our matrix and write the augmented form of it to solve the homogeneous system to find the eigenvector x. After we've got all eigenvectors and eigenvalues, we can write the form of fx. So c1, c2 up to cn are just the constants, and x1 is the eigenvector corresponded to the eigenvalue lambda 1 here. And then we can apply the boundary conditions to determine the constants. So f1 at A equals to b1, f2 at A, and fn at A equals to bn, where we know that this column vector is just, f at A, and we know that f at A is just replacing x with A. So yeah, this is our equation equals to this. And we can write this as the matrix multiplication. We can solve for each of these entries from the augmented form of this one, and then we can find the constant after that. So for example, if we want to find a general solution to the system, the derivative of f1 equals 2f1 plus 4f2, and the derivative of f2 equals to f1 minus f2 with the boundary conditions f1 at 1 equals 5 and f2 at 1 equals 3. First construct the coefficient matrix A, and then setting the determinant of lambda I minus A to 0. So the determinant is calculated by lambda minus 2 times lambda plus 1, and then minus the product of minus 4 and minus 1, which will give us 4. And then so just distributing these in will give us lambda squared plus lambda minus 2 lambda is minus lambda, and then minus 2 minus 4 will give us minus 6. And then we will split this minus lambda into 2 lambda minus 3 lambda for the purpose of factorizing this out. So if we factorize lambda out, we'll get lambda plus 2, and factorizing minus 3 will give us lambda plus 2. Eventually, lambda minus 3 times lambda plus 2. The roots of this equation are lambda 1 equals to 3 and lambda 2 equals to minus 2. With eigenvalue lambda 1 equals 3, we can substitute that into our matrix. This will give us 1 and this will give us 4. And if we multiply minus 1 to the second row, then it will be the same as the first row. So we can remove the second row, and then we'll keep the first row as this. So if this is the coefficient of t, then we can move this to the right, which will give us 4t, and factorize t out, which will give us 4 and then 1. So this is also the eigenvector x1. So the same for lambda 2, that is equal to minus 2. We can substitute minus 2 into our matrix, and first row is equal to the second row. So when we remove the second row, and then we can turn the first row to 1, 1, 0 by dividing the whole row by minus 4. If this is t, then this will be minus t, and so factorizing t out, which will give us minus 1, and this is 1. So the basic eigenvector x2 is minus 1, 1. We can write fx based on the calculated eigenvalues and eigenvectors. So this is c1 times the eigenvector x1 is 4, 1, and then e to the power of lambda 1, which is 3, and the same for this term here with x2, the eigenvector minus 1, 1, and the eigenvalue minus 2. We can apply the boundary conditions to determine the constant. So f11 equals to 5 and f21 equals to 3. Because this is the color vector f1 and we have written in this form, we are now just replacing x with number 1, which will give us this form, and then we can write this in the matrix form. With the augmented form, we can swap the first row and the second row and then subtract 4 times the first row from the second row. That will give us this one, and then we can divide the second row by minus 5 to get a 1 here, and then use this one to eliminate above entry, which will give us a 0 here. So this one here is the coefficient of c1 times e to the 3. We will have c1 e to the 3 equals to 8 over 5, and the same for c2 times e to the minus 2 will give us 7 over 5. So moving e to the 3 to the right will give us c1, and moving e to the minus 2 to the right will give us c2. And with the calculated c1 and c2 along with our fx, the general solution for f1 is equal to c1 times 4 times e to the 3x, which will give us this, and then c2 times minus 1 times e to the minus 2x will give us this one. And the same for f2, c1 times 1 times e to the 3x will give us this, and c2 times 1 times e to the minus 2x will give us this. So thank you for listening.